Now let us say given a max heap, I want to delete the maximum from it. So take an example and I'll show you. Say the example is like this. Say this is a max heap. Is this a max heap? See this? It is a max heap, right? Now what we want to do is we want to extract the maximum. Okay, which means, see, first of all, if this is the max heap, how will this be represented in the array? In the array you will see that it will be present in the first index 50 and then 20 and then 1, 3, 10 and then 5, right? Therefore the first element is this, second is this, third is this, 4, 5, 6, 7, right? All the 7 elements are present there, right? Now directly straight away, if someone asks what is the maximum, you can just return the first element, that is going to be maximum element, right? So finding the maximum is just order of 1 time, but what I wanted is I want to delete it from the tree. I want to delete it. If I delete it, then there is no, if I directly delete it and leave a gap here, then it is not a complete binary tree, right? So it has to be almost complete binary tree. So I cannot just simply delete it and leave it there. So what I should do is, see what this algorithm will do is, I'll show you with this example. It is going to delete the first element, yes, the root, which is maximum, and is going to return to you, and you are going to get 100 is the maximum. And now it is going to go to the end and take the last element. Okay, here the last element is 5 and make it the root, right? So previously this one was complete, this one was max heap and this one was max heap. Now the left subtree is a max heap, right subtree is a max heap, but the root is not following the max property. Then we already know that we have to call the max heapify function on this. So I am going to call max heapify function on this, right? So when I call max heapify function, what will it do? Initially the function call will be made here, then it will compare these three. Which one is maximum? 50 is maximum, therefore it will be exchanged. 5 will be here and 50 will be here. And again at this point max heapify will be called. Which one is greater? 5 is greater, therefore it is going to stop there, right? So whenever you want to delete maximum, you are going to call max heapify, and then we are going to delete it and put the last element there, and we are going to call max heapify, right? See this? Now again if I want to delete maximum, then delete it. So what is it? 50. So you got 50 as the next number, and take the last element. What is the last element? 10, and we are going to put 10 at the root. Okay, now we got 10 at the root, and now we apply max heapify. So if I apply max heapify, which one is maximum? 20 is maximum among these three, therefore 20 will come here, 10 will come here, and again max heapify on this. Since there are no children, it will stop, right? And let us say I want to delete maximum again, then what will happen? Again you delete it, we are going to write 20 here, and what is the minimum of this? The last element of this, last element is 3 will be placed here, and again max heapify will be called on this, which means compare these three, which one is largest? 10, therefore you put 10 here and 3 here. That is how max heapify is going to work. And next one is, again if I want to delete maximum, then again you are going to delete the maximum. We are going to say that we got 10, and we are going to put the last element here, which is 1, right? And then we can again apply heapify, then I get 1 here, 5 here, right? So one thing you should observe is, in order to delete one element from the max heap, the total time required is just just to call the max heapify. So I'll just explain you how this algorithm is working. See this? Now the initial given input is 100, 50, 20, 1, 3, 10 and 5. This is the input given, right? If this is the input given, so what does the first one do? It will check that this line will check if the heap is having at least one element. If the heap is not having at least one element, then the heap size will be less than 0. Then obviously it is, we cannot apply anything on that, right? And the next step is, we have to find maximum. So what is maximum? Maximum equal to a of 1, right? So which means this is being stored. So maximum equal to a of 1 is 100, right? and next one is a of 1 equal to a of heap size. In this case, what is the heap size? 1 2 3 4 5 6 7, right? Therefore heap size is 7. Now a of 1, which means this one, is equal to a of 7. So this 5 will be written here. It is nothing but taking the last element and writing it over there, right? And now we have to decrease the heap size, isn't it? Previously the number of elements in the heap were 7. Now the number of elements in the heap were 6. That is why you decrease the heap size. Now whatever I did, they are all constant time, constant time operations. So till this part everything is constant time. And now we have to call heapify on this. So whenever I call heapify on a node, then the time taken by that heapify is max heapify function is, we have already seen that is order of the height. Then what is the order of the height of what is the height of this tree? It is nothing but order of log n. Why? Because we are calling heapify always on the top. We are calling the heapify always on the root of it, right? That is why it is going to be order of log n. So understand this. The total time taken by this algorithm is total time taken till this part, which is constant, and then time taken by this, which is order of log n. Therefore constant plus order of log n is order of log n. So this is the time taken by this extract max. And what is the space taken by this? We are not using any extra space other than the variable max, right? So constant time, and whatever is the time space taken by the max heap. So what is the space taken by max heap recursion? We have already seen that max heap might call log n times. Therefore space complexity is also order of log n. So time complexity and space complexity are both order of log n for extract max. Okay. So this is how we could delete extract maximum from the max heap. And the same thing could be done extract min from the min heap, right? So with minor modifications you could implement it, right? Now let us say this is one more supported operation. Given a max heap and a node in that, I want to increase the value of that node. So see this example. Let us say max heap is this. Something like this. Okay. Now I want to increase the value of a node. So how does it look like? This is index is 1 2 3 4 5 6 7, right? Now I want to take one node and I want to increase the value of that node to some higher value. Let us say I want to increase the value of 3 to 300. Then what happens? Let us assume that this 3 is increased to 300. Then we are going to call increase a of, what is the index? We are going to increase inside the array a the fifth index to 300. Okay. So from 3 I have to raise it to 300. Then what happens is, if I raise it to 300, there is a chance that this value might be greater than the parent, right? But then what is that we are supposed to do? Always in a max heap, parent should be the largest element in the subtree. But here the value of the parent will be lesser than this. Therefore we are supposed to exchange. So I have to exchange 300 with 30. Then what happens? Then again this value may be greater than its parent. So I should keep on checking with the parent till I reach the root. So if I see this value is definitely greater, therefore this one has to be exchanged. Got it? Isn't it? Now let us say I want to increase the value of 10 to maybe 100. So if I increase 10 to 100, then what happens? I should compare with the parent, and then if it is lesser I should swap it. Therefore it is lesser, so parent has to be here and 100 has to be here. And again 100 has to be compared with the parent. If it is lesser I should swap it, but then it is greater, so leave it there, right? So that is how the algorithm is going to work. See this? Now whatever value you are going to increase, that should be greater than the initial value, otherwise it is an error. It says that, the first line says that you could increase the value of a of I, but then before increasing it, see that you are not actually decreasing it. So this algorithm is written for increase the key, not decrease the key, right? And then what is the next step? You have to take that whatever the value is, you are going to substitute there in that value, and then we are going to check with the parent. This is what I by 2 means the parent. If a of I is the node, then what is its parent? A of I by 2, right? If a of I by 2 is less than a of I, which means if parent is less, then we are going to exchange, right? And why is this step used? This step is used to check whether we have reached the root or not. Once you reach the root, there is a chance that you might try to go beyond it. See, you are going from here to here, here to here, and you are supposed to stop there. That is why this step is used. We are never going to go beyond the root because there is nothing there, right? And now this step is going to check if the parent value is greater than the child. If the parent value is less than the child, obviously they have to be exchanged. The reason is it is a max heap, right? So if the parent value is greater than the child, they will be exchanged, right? And then finally I equal to I by 2, and the same thing has to be done again here, right? Which means once you write a value from here to here, again you have to check it with the parent. So in this sense, if I have a tree like this, okay, now if you increase the value of this, you have to check with this, and after swapping this, you have to check with this. Anywhere if you see that it is fine, then you can stop there. Which means if anywhere you see that the parent value is greater than the child value, you can stop there. Otherwise you keep swapping it and again checking there, keep swapping it again checking there until you reach the parent, right? So that is how increase key is going to work. So increase key is going to start at one node and it is going to rise till the top. Therefore, how many times this while loop may execute, that is going to be the time complexity of this algorithm. In worst case, you might start this increase key at a leaf, and it might try to go to the root. Then we know that the height of the tree is nothing but order of log n. Therefore, we might need order of log n time to start from here and compare swap. For that we need order of log n operations, right? So that is how we are going to work on increase key. What about decrease key? If I want to decrease the value of a node to some value, so is it permitted? It is permitted. Either it is max heap or min heap. You can do both increase key as well as decrease key. See, on the max heap you are doing increase key, right? And on the max heap itself you could even do decrease key. Let us say I want to decrease the value of this key 300 to maybe 3. Then what should we do? How should it work is simple. Now after decreasing a value of a key, the left subtree is a max heap, right subtree is a max heap. So therefore decreasing the value in a max heap is nothing but replacing that value with the new value and then calling the max heapify function. The reason is left subtree is already a heap, max heap, right subtree is already a max heap. Now the root is not a max heap. Therefore decreasing a key is also calling max heap. Just replace that value and then call max heapify procedure. We have already seen that, right? Then what is the time for decrease key? It is going to be order of log n, isn't it? In worst case, if decrease key is called on the parent, the top, the root, then it is going to climb down till the leaf, and we have seen that the time complexity required is order of log n. And in this case, the space complexity required for increase key is order of 1. The reason is we don't have any recursion here. We are just implementing it using iterative version, right? And if I use the recursive version, then it might go to order of log n. But since the function is recursive, you need not go for iterative. We need not need order of log n time, right? So one thing you should remember is, if on max heap I am going to do decrease key, it is nothing but max heapify, right, which is going to take order of log n. And if on max heap I am going to do increase key, then also it is nothing but order of log n. The reason is it will rise up, right? So increase key is going to rise up, decrease key is going to come down. Okay. Now we shall see how to use this increase key in order to insert an element into the heap. Okay. Let's see how to insert an element into a max heap. So take this example of max heap. Where the max heap is something like this. Okay. Now this is the max heap. I want to insert an element into this. So how could we do that? So insert the element. So whenever we want to insert the element at the last position. Let us say the element that has to be inserted is 200. 200 is inserted. After inserting it, now compare with the parent, right? Then if it is parent is lesser, swap it. Then what do I get? 1 here and 200 here. And whenever you swap it, again compare with the parent. If parent is lesser, swap it, which means 20 here and 200 here. Again you compare with the parent and swap it. If it is lesser, you swap it. 1 here, 200 here, right? Therefore you are going to stop there. Therefore, how is insertion going to work? We are going to insert the element at the end and then we are going to swap it with the parent. Then what is the total time complexity required for it? So in worst case, a element might have to travel from the leaf to the root, for which the time complexity taken will be order of log n. Therefore the time complexity for this algorithm is order of log n. And already we have seen that decrease key, right? In this case, I think we have seen the increase key. Already we have seen the increase key just now. We could even make use of that increase key in order to implement this. Since we have already written that function, it is better to make use of it instead of writing one new function. So how to use that increase key function in order to insert an element is, let us say I want to insert the element 300 into the list. Then what I do is, at the new node, I am going to insert an element minus infinity. Minus infinity means some element which is very, very less than all these elements. I mean, whatever data, if you are using int, you see the range of int and you take the least smallest number in the implementation. Okay, the largest negative number. Then let us assume that already minus infinity is there. Then it is simply increasing the value from minus infinity to 300. So we can call increase key. Increase key means this one will be replaced with 300 and the same function will be called. So what will happen? 300 will be compared with 20. We found out that 300 is greater. Therefore 300 will go there and 20 will come down, isn't it? And now 300 will be compared with 100. Therefore again it is greater. So 300 will go up and 100 will come down. And again 300 is compared with 200. Therefore 200 will come down and 300 will go there, right? Therefore, in order to insert an element, one element into the heap, the time taken will be log n. Okay, so this is how we can do various operations on the heap. So if you just understand, if you just see what are the various operations that we have seen on a heap, we shall just see what is the time complexity required by this. Let us say the given heap is max heap. On a max heap, if I want to do find max, if I want to find the maximum element, directly the first element is nothing but the maximum element. So it is going to take order of 1 time, constant time. If I want to do delete max, if I have to delete max, then what is that we are going to do? Delete the maximum and take the last element and put it at the top, and then we are calling heapify. So for which time taken will be order of log n, isn't it? And let us say I have to insert an element. Just now we have seen that insertion is going to take order of log n, and I have to decrease the key or I have to increase the key. So we have seen that increasing the key is going to take order of log n, because in worst case we might try to increase the value of a leaf and the leaf might try to travel to the top. Therefore it is going to take order of log n. And let us say we are going to decrease the key, decrease the value of a key, and we have seen that if we decrease the value of a key, left subtree is going to be a heap, right subtree is going to be a max heap, but the value of that root may not follow the max heap property. Therefore we might have to call max heapify function, for which time taken will be order of log n, right? And now apart from this, these are the operations which are going to have the optimal performance, which means these are the operations for which heaps are actually built, to delete the maximum, insert an element, increase the key, decrease the key, and find maximum, right? And if you try to do anything other than this, for example, on a max heap, if I want to find minimum, right? these such operations will take more time. The reason is this is optimized to find the maximum, and if you want to find the minimum, you might have to search the entire list. It is as good as the ordinary linked list, ordinary array. And one thing is for sure, definitely the minimum will be present in the leaves. Therefore you have to search only at the leaves, but still leaves are going to be order of n by 2, isn't it, which is nothing but order of n searches are required. So finding a minimum is going to take order of n, and if I try to delete any element, right, if I try to delete a random element, then also it is going to be not very feasible. The reason is this value is going to entirely spoil the, well, if I delete any value from the middle, that is going to entirely spoil the property of the heapify. Therefore we might have to again build the heap. So it is going to take order of n. You can delete an element, search for it. Okay, before going to that, delete, let us say searching a random element, not the max or not the min. I want to search some element. So searching element is going to take order of n time. The reason is if I want to search any random element, heap is as good as an array, right? Therefore it is going to take order of n time. Let us say I want to delete an element. So for the deletion, first I have to search, for which time taken is order of n, and after I delete an element from the array from a random position, the entire heap gets disturbed, isn't it? Therefore again you have to build heap, for which time taken will be order of n. Therefore total time will be order of n. So any operation other than these operations, if you try to perform on heap, the time taken will be more. So heap is optimized only for these operations. So you are supposed to use heap if your problem actually requires finding max or finding min, in case of min heap, right? If your problem requires only these operations, then go for heap. If your problem requires both of these, then you might have to search for some other better data structures. Okay, so now this is how this is about the heap operations. Let us see how to implement heap sort using the heap data structure.